Welcome. We are in Unit 8, and today we finish Unit 8 with Day 3, a library of functions. This is section 3.4 from the book, and we will cover the entire section. So the first objective is to graph the functions listed in the library of functions, and the second objective is to analyze piecewise defined functions. The library of functions. Here are 8 fundamental functions. You really need to know what these functions look like and how they behave. Over the course of this video, I'll go through each of these functions one by one, and we'll see some of the characteristics of them. Then at the end, there's a test yourself section, so see if you can recall what these functions look like without looking back at your notes. All right, let's take a look. The first is the constant function. A lot of times we'll have a function that looks something like f of x equals 5, or f of x equals 2. That's called a constant function. In the graph here, they just wrote f of x equals b. What would the graph of f of x equal 2 look like? F of x equals 2, so I know that f of 1 equals 2, and f of 3 equals 2, and f of negative 1 equals 2, and f of 17.3 equals 2, on and on and on. F of anything equals 2. So if I were to graph that, then when my x is 1, my output is 2. And when x is 2, my output is 2. When x is 3, the output is 2. When x is negative 1, I get a dot there. When x is negative 2. So this constant function is just a horizontal line that is the height of the constant. And that is the constant function. The identity function is the next simplest kind of function. See this, it's just f of x equals x. For example, we have f of 1 equals 1, and that's what's plotted on the line there. F of negative 1 equals negative 1. There's another dot on the line. But also things like f of 17 equals 17, f of negative 34.9 equals negative 34.9. And it is just kind of interesting that this identity function, f of x equals x, looks like it does. It's just the nice straight line goes through the origin at a 45-degree angle, and every value of x, for example 3, comes up, hits the curve, goes across, and is matched perfectly with the 3 in the y-axis. There is the identity function, f of x equals x, nice straight diagonal line through the origin. The square function, after that, this is f of x equals x squared. And we've seen this before. We studied quadratic functions and some polynomial functions. Related to this are the x to the 4th curve, which is just a little bit flatter, and then maybe higher powers, x to the 6th, which is flatter still. Try to draw that like that. There we go. But take a look at the picture. This is our standard nice parabola, and look how the points obey the law of the function. So if f of x equals x squared, then f of 1 equals 1, f of 2 equals 2 squared equals 4. If I were to draw a 3 there, f of 3 is 3 squared equals 9. So at 1, 2, 3, if I were to draw this all the way up until it hit the curve, it would hit way up there at 9. And, I mean, of course you can keep on going and going. F of 10 equals 100. And so this graph just goes up and up and up forever and ever. It's a nice parabola. Also, another function we've seen before, the cube function, and its relatives, x to the 5th, x to the 7, and so on. Now, what does the cube look like? F of x equals x cubed. So I can plug in f of negative 1. Oh, look what happens with the negative 1. When I cube negative 1, it's like negative 1 times negative 1 times negative 1. It's not positive anymore. It's still a negative number. And look how we see that on the graph. F of negative 1 is negative 1. F of negative 2 is negative 2 cubed. So negative 2 cubed, negative 2 times negative 2 times negative 2 is negative 8. And can you see where that would be on the graph? It's not plotted, but you can imagine following that graph down a little bit further. And similarly, in the positive direction, f of 1 is 1 cubed equals 1. F of 2 is 2 cubed equals 8. And if I continued, f of 3 is 3 cubed, which is 27, so that's way up there. And then 4, I see 4 on the graph. F of 4, how big would that be? F of 4 is 4 cubed, which is 64. So that is way up there. This graph grows very, very quickly. The cube function. The square root function. So imagine our nice square function, the parabola, but instead of drawing the parabola straight up and down like this, you draw a parabola on its side. Well, the square root function is just the top part of that sideways parabola. So it really is nice, it really has kind of the same shape as the parabola, just tilted on its side and only half of it. Now with the square root function, f of x equals square root of x, some numbers work nicely, like f of 1 is the square root of 1, which is just 1. But a lot of other numbers don't work as nicely. F of 2 is the square root of 2, but the square root of 2 is not a nice number. I mean, it's approximately 1.4. Maybe we can see that in the diagram. If I had a 2 on the x, and I come up, that y value is about 1.4. The next nice point doesn't occur until f of 4, because now I know the square root of 4 is 2. And then after that, I guess we'd have f of 9. Square root of 9 is 3. So if I took this graph out, oh, maybe I could do it all the way to 9, then I'd get my next point on the graph, follow it up, square root of 9 is 3, so somewhere around there, and the graph would go through it. So that is the square root function, and that's what the graph of the square root looks like. The cube root function, this is interesting because it's not just half a graph like the square root was. The cube root is a full function itself. Now recall the cube function looks a little bit like this. And if you took that cube function and you draw a diagonal line, maybe the identity graph, right? And you were to flip the cube function over that diagonal line, what you'd end up with is the cube root function. So the cube root function has exactly the same shape, the same kind of curve as the cube function, just tilted over on its side. Now, some funny things happen. It's hard to get some good points on this graph, but I do know, let's see here, f of x equals the cube root of x. I do know a few cube roots. The cube root of 8 is 2, because 2 times 2 times 2 is 8, so the cube root of 8 is 2. Here, maybe I'll draw it like this. The cube root of 8 is 2. And of course, 1 works nicely. F of 1 is the cube root of 1, because 1 times 1 times 1 equals 1. There's not much else. I guess 0 works. In the picture, they have 1/8 and 1/2 listed, because let's see, if I take 1/2 and I cube it, so that's 1/2 times 1/2 times 1/2, I end up with 1/8. So the cube root of 1/8 is in fact 1/2. And that's what's pictured in the diagram. The point is at 1/8, 1/2. But mostly, the trick is just to remember that the shape is the same as the cube function, just tilted on its side. Now we have the reciprocal function. This is the graph f of x equals 1 over x. So if I plug in f of 3, I get 1/3. F of 5 is 1/5. What if I keep going out? F of 10 is 1/10. F of 100 is 1/100th. As this graph goes to the right, the y values get smaller and smaller and smaller and smaller, and they always get closer and closer and closer to that x-axis, but they never actually touch the x-axis. Now, as the x values get really close to 0, look at this, it really shoots up. It gets bigger and bigger and bigger. It starts to hug the y-axis up there. And then something on the negative side is going on as well. If I go out way to the left, the graph will sort of hug the x-axis, and if I go really close to 0 on the negative side, then the graph will hug the y-axis. But notice in particular that this function is not defined at 0. So f of 0, which would be 1 over 0, does not exist. I just can't graph the function there. So that's why it's missing from the graph. The absolute value function. This rounds out our library of essential functions. We've worked a little bit with the absolute function, but we haven't actually graphed it. So here it is. It's just a nice V shape with the arms going out at 45-degree angles. You know, the absolute value of 2 equals 2. This acts a lot like the identity function for positive values, right? Absolute value of 5 equals 5. Absolute value of 17.3 equals 17.3. So it really is the same as the identity function, as long as my x values are positive. And then for negative x values, it's like the identity flipped over. So absolute value of negative 2 equals positive 2, and I can see that plotted in the graph. Absolute value of negative 1 equals 1, and so I see the point negative 1, 1 plotted there as well. Okay, the time has come to test yourself. Put away your notes, pause the video, see if you can reconstruct from memory these 8 functions. All right, go to it, pause the video, and then start it up again when you are ready to check your work. Here we go, the big reveal. There it is. How'd you do? I hope you did all right. Actually, I do hope you did all right, because I'll say it again, these are fundamental functions, and it helps your intuition when working with functions. It helps your intuition so much if you can just pull these out from memory without having to search too hard for them. Let's move on to the next big topic, which is piecewise defined functions. Here's an example of a piecewise defined function. F of x equals negative 2x if x is less than 0, and square root of x if x is greater than or equal to 0. So maybe let's focus on the domain restriction. That's what we have after the if. So if x is less than 0, then the function will look like negative 2x. So you see, over this region where x is less than 0, if I look at that function looks like negative 2x. And if I look at the part where x is greater than or equal to 0, here's the part of the x-axis where x is greater than or equal to 0, then that function, that is the square root function. Do you remember the square root function, right? Just like that. And that's what we see in the graph there. Let's do a couple examples where the function is given to us and we have to graph it out. First example, f of x equals 3 plus x if x is less than 0, x squared if x is greater than or equal to 0. If you think you know the answer, then pause the video and give it a try. Otherwise, here we go. First, I'll focus on x less than 0, so the left part of the x-axis. Over that, I will graph the function 3 plus x. What does 3 plus x look like? So let me just write this out separately. F of x equals 3 plus x. So maybe f of, oh, you know, I was going to put f of 0. Well, what is f of 0? F of 0 equals 3. F of 1 equals 4. And let's work backwards also. How about f of negative 1 equals 2. F of negative 2 equals 1. All right, and let me plot those points. F of 0 is 3. F of 1 is 4. F of negative 1 is 2. Oh, I think I see a pattern. F of negative 2 is 1. There we go. So it really is a nice straight line. Of course, 3 plus x. Now you might have been able to do this by using graph transformations. You know that the graph of x, f of x equals x, that's the identity function. That just goes through the origin, but then x plus 3 takes that and shifts it up 3. Right, so I'm doing pretty well, except I've sort of overextended my graph. You see, this graph is only supposed to be defined for x less than 0. So I need to erase some of that graph that I've drawn. So how about we'll erase some of these points, redraw the line here, and I'm getting close to the y-axis. I'm going to put an open circle because I'm not actually graphing onto the y-axis because of that strict inequality. The graph is only true when x is strictly less than 0. Now let's move on to the second condition on my domain. For the second part, I want to focus on where x is greater than or equal to 0. So that looks like the right part of the x-axis. And for that, my function is x squared. Oh, so x squared is in my library. I know what x squared looks like. Let me go ahead and just write out x squared. Put a few dots down there. But once again, I don't really want all of x squared. I only want x squared when x is greater than or equal to 0. So let me erase the parts that I don't really want. This should be defined also at 0, so I really can put a solid dot right at 0. I know that f of 0 is 0. And I think that's it. We've graphed successfully this piecewise defined function. Let's take a look at another example. In this example, my piecewise defined function has 3 pieces to it. So let's take each one separately. The first part says, let's look at x's that are greater than or equal to -3 and less than 1. So I'll highlight that part on the x-axis. There we go. And I want the graph -2x plus 2. Well, thinking about graph transformations, the graph of -2x, that's a line that has slope -2, and the plus 2 shifts it up 2 units. So I'm going to put a dot at 2, and then I'll make a slope of -2 from there. And so connecting my line together looks something like this. So that's the graph of -2x plus 2. But of course I don't want the whole thing. I just want over this domain. So I need to erase part of it. Oops. Actually, yeah, I need to stop at the -3, right? It doesn't actually go on to negative infinity. There we go. So that looks pretty good. Now what about closed dots or open circles? I think I want an open circle here at the very right side, because I don't include the 1, but it should be a closed dot, sort of a completed dot there on the left side. All right, so that is the first part. The next part is kind of funny. It's just a single point. If x equals 1, the value is 2. I have a constant function. So at 1, I will make a point of height 2. There we go. and that completely handles the second part of this piecewise defined function. Moving on, the third part says if x is greater than 1, so everything to the right of 1, then the function looks like x squared. Ah, there's x squared. I've drawn that a couple times now, so let me draw my x squared function. And at this point, I will erase the stuff I don't need. Sorry, that was such a nice looking parabola. Oh, I need to erase... okay. How about if I... it's just to the right of that 1. There we go. Looks something like that. And I think I have completed it. Now, take a look at the open circles. I have, with the green graph, this x squared, there's an open circle at 1, and with the blue graph, there's the open circle at 1, because the dot, the red dot at 1, fills in the picture there. And that's it. There is our picture for this piecewise defined function. So in this video, we've hit 2 big ideas, this library of function and piecewise defined functions. Once again, I cannot emphasize enough the importance of this library of functions. Go back and test yourself again if you need to. Know those 8 graphs cold, because those graphs are mixed together and changed and moved around. They form the components of basically every other graph that comes after this. So that is important. Then you can see in the piecewise defined functions, we used some of those fundamental functions as parts of the piecewise defined functions. All right, that's it for this video.